Welcome to the Creative AI Podcast. Something that we often take for granted as humans is the ability to look at an object and have an approximately correct mental model of its 3D shape. For example, if you were to see a small image of a steering wheel, you'd probably have a fairly accurate statistical representation of the other aspects of the car. You'd have a pretty good guess of where the driver might be, the engine, the four wheels, etc. However, this intuitive approach for humans is difficult for machines. Therefore, we need to develop techniques to pass this information to machines. The faster, easier it is for us to do this, the more quickly we can leverage this technology in its widespread applications. These researchers are working on improving just that. Their work is taking 2D imagery and generating 3D representations of the object. This is incredible work, and I'm super excited to see better, faster ways of inputting 3D data into a world that we're starting to explore with things like augmented and virtual reality. I'll have them explain more. Let's hop into the show. Hey guys, read your research paper, Weekly Supervised Generative Adversarial Networks for 3D Reconstruction. There was some really cool kind of ideology, but quite frankly, I couldn't quite make out exactly what was going on. And so I'd love for you guys to kind of explain the research in your own words.
All right. So I guess this is Junior, and I'm Chris, and then probably Junior can provide a high-level overview of the paper.
Okay, sure. So 3D reconstruction in the first place is one of the core problems in computer vision. And the problem set was quite simple. So given a 2D image, can we infer 3D information about it? And while human can handle this problem quite easily, it is a very difficult problem for computers because there are a lot of information lost by 3D becoming folded down into 2D image. And there are a lot of research done in this field trying to make a better sense of how the 3D world is working behind this given 2D image. And our focus is in one of these 3D reconstruction fields, trying to reconstruct a single 3D model when we take a picture of, let's say, for example, like a car. It can be very useful in various fields. For example, on Amazon, if somebody wants to sell some product, let's say he wants to sell like iPad, then if he takes a picture of his iPad, then people might be able to look at if we can 3D reconstruct that person's iPad, then we can give users like a better experience, letting customers like play around with the 3D model of the actual item that is going to be sold and stuff. So 3D reconstruction by itself is a very interesting problem, but also a very challenging problem because there are a lot of information lost behind 2D image. And it's our job trying to make the computer make better sense of these 3D information out of 2D image. And while there are a lot of classical techniques, there's a huge background of history behind this. The neural network has made huge advance in 3D reconstruction field as well. And one of the first papers to make the 3D reconstruction into neural network was called 3DI212, which is a paper by Chris, a co-authored also by me. It's just we're teaching the neural network given 3D model and its 2D image. Telling the network, okay, I'm going to give you 2D image. Now try to make a best guess at the 3D model of this 2D image. So we've gone through these, and there are a lot of following and concurrent researches regarding this field, trying to give 3D model and 2D image, and trying to teach a network that better reconstructs 3D model given 2D image. But we tried to focus on something a little bit different in this paper. That's although it is, first of all, as you might know, the neural network, when you're trying to train it, requires a lot of training data. It is very data hungry. And in order to train a network to reconstruct 3D model, that means that it requires a lot of 3D models and 2D image pairs. Well, this is a very expensive annotation. Because if you think about it, if you are given a random 2D image, do you think you can easily retrieve a ground truth 3D model corresponding to a 2D image? It's actually quite a difficult problem. And so this setup in first place is quite unreal in practice. And we thought it is bottlenecking hugely from what is making the 3D reconstruction useful in the real world. So we try to focus on something a little bit different, that instead of trying to teach the neural network to reconstruct 3D by giving the neural network 3D model, is there any way to tell the neural network, like, is there any better way, a different kind of supervision, a different kind of data that we can provide to 3D to a neural network to let it learn the 3D reconstruction? And a line of focus was made by trying to give a neural network 2D mask to the silhouette of an image, and also giving a camera some camera information. For example, okay, we are looking at a 3D model. You're given a 3D model here, and we have a camera looking down into this direction from one direction. Then, if you know the silhouette of the image, then, well, this is by the way quite a known problem in computer vision. It's a very traditional technique. Also, like using things like voxel carving. It's its own set of problem that we can, and it is very known that we can reconstruct 3D models given silhouette of an image and its camera parameter. So
can I hop in and ask you a question here? So the idea is like take a photo, and so I'm like looking at the research paper of this red cow or this red chair here, and then there's the silhouette part of it or the mask of it. And then the camera parameters, and some of those parameters, what would be an example of some of those parameters that you were talking about?
So we focus on the extrinsic camera parameter, which is like camera positions. For instance, like how far the camera is from the instance, and then what's the angle that the camera is looking down, and then how far this camera is away from the center of the chair. Those are called as extrinsic camera parameters, and then we use that information to do the ray tracing.
Cool. And are there certain cameras that have more or less information? I would imagine an iPhone, for example, or at least the newest iPhone has the dual cameras. It has a accelerometer in there. Are there cameras like that help with things, or is this kind of other types of cameras that have that type of data?
So yeah, some recent cameras have like dual cameras, which means that you have stereo vision. So that means that you can take a picture of an instance from two different viewpoints. This gives a bit more information than just a single image, because you can find the depth by triangulating the point using these two viewpoints. But in our setting, we only restrict it to like a random viewpoint. So for instance, in Amazon or eBay, users just to take a picture of a product from random viewpoint, and then since we don't want to make any assumption about the distance between two images, like stereo vision,
right.
We just didn't restrict our setting to a specific cameras, and we allow the network to figure that out by itself by just using the extrinsic camera parameters and just a silhouette annotation.
Okay, cool. Yeah, thanks for helping clarify that.
So I guess to summarize what Junyoung said, in the 3D R22, which is one of the first works, if not the first, that explored the supervised 3D reconstruction. 3DR2 is an acronym for Recurrent Reconstruction Neural Network. So in that work, we explored a multi-view reconstruction that some of the traditional method failed. For instance, some of the traditional method, like structure from motion, have strong assumptions about the distance between cameras and so on, so that it usually is very difficult to reconstruct an object. But we want to get away from this kind of restricted setting by using a supervised 3D reconstruction, and then we use the neural network as a machine learning tool that allows us to do the supervised training. However, the problem with this setting is that we need the 3D CAD models. So we need the ground truth 3D reconstruction, as the neural network usually requires such annotations. Um, but this is a very expensive annotation to gather. So, for instance, if you use the Amazon mechanical turpers, and they have to see like 50,000 cat models and to pick the best one that matches the image. So it's a very extremely expensive annotation and almost impossible to get. So instead of just feeding the neural network what this 3D model exactly is, we want to use a weaker form of supervision, which is 2D annotation. However, the 2D annotation itself cannot do the 3D reconstruction. So, for instance, in Figure 1, we demonstrated what the silhouette can and cannot do. So, in the Figure 1 of the paper, we used the silhouettes up to 24 views to generate the 3D reconstruction of a chair. Sorry, Figure 2.
Figure 2, all right.
So in the Figure 2, we present a chair, ball type chair, that has a concavity inside the chair, and then we show that even when we have like 24 masks, it's impossible to reconstruct this concavity because the silhouette itself is a weaker form of supervision, and that it can only reconstruct a visual hull. So to get away from or to improve this kind of lack of information, we use the disc-grainer as a manifold projector. So if you could go to further down in the it's further down in the disc-grainer section. Yes, that one.
Did I go past it here?
Yeah, you went past.
Oh, sorry. All right.
All right,
Edit that out.
Figure 5. Yes. So in Figure 5, we just visualized what the discriminator learns. So if you think of the generative adversarial network, in generative adversarial network, probably I should explain what the generative adversarial network is first, I guess.
Yeah, that'd be great.
So in a generative adversarial network, you train a discriminator and the generator in an adversarial way, so that the discriminator try to distinguish what the real versus the fake one. So if you can interpret this discriminator in another way, that that the discriminator has a higher value when the input is close to the real image or real shapes or etc. Or the data type, and then to have lower generates produce lower value if it's far away from the realistic shapes or whatever the input image input data is. So that means that we can interpret this as a sort of a probabilistic distribution that have higher value on the real space, and then the lower value on the non-realistic space. And then we presented, demonstrated this in the Figure 5, and then to show that if the discriminator takes a realistic shape that doesn't have any artifact, it will achieve higher value, whereas if we feed in a random values, then it will generate a very low value. So if we take the gradient of the output of the gradient with respect to the input x, then this gradient will guide the input to the higher region. The region where the realistic space shapes lie. So we visualize this in the arrow in the Figure 5. So basically, if we take the gradient of the log discriminator x with respect to x, then this gradient will provide some projection, some gradient toward the realistic region. And we can think of this as a manifold projector.
Interesting. And so some of these, obviously, so the one at the red is we were talking about kind of at the peak of this have this piece, and like what is this one with the kind of the green and partial? It's like it looks like a local maxima somewhere else, but obviously not the global maxima. Like, what does that one kind of represent to you?
So we used other colors to visualize the probability of each voxel being occupied.
Got it.
As it gets closer and closer to 1, we use the red to visualize this voxel being occupied, and then if it gets greener or blue, then it has lower probability.
Interesting. Thanks.
We use this as a manifold projector, and then try to minimize both the generative adversarial loss plus the reprojection loss. So to explain the reprojection loss, probably I should explain more about the figure 4, or maybe Junyoung. I think Junyoung can explain this better.
Sure. Yeah. So in figure 4, we visualize our perspective ray tracing pooling layer. What this does is when you're given, so in the neural network there are a lot of mathematical operations going inside the neural network. Probably the most famous one will be convolution, and there are various kinds of layers like fully connected layers and such that applies various kinds of mathematics inside the neural network. And while these do generalize quite well to various problems like classification, segmentations, and stuff, there are some set of operations that cannot be done. Some set of problems that cannot be solved only using these operations. So instead, we propose a new layer that is able to handle a different kind of operation that we want to solve. That is given a 2D silhouette and also given camera parameter. So can we figure out? We've talked about this the camera relationship with the object using camera parameters slightly before. Can we actually encode this mathematic directly into the neural network? That was what we wanted to solve from this perspective ray trace pooling layer. And this perspective ray trace pooling layer explicitly computes the physics behind the camera, how the ray goes through the voxel space, and checks whether if it hits within the voxel or not, and accumulates all of the scores. So it essentially, you can think of it as a camera, you can think of it as a physical camera that is taking a picture on the voxel space that we want to reconstruct, and it will give you a 2D projected shape of the 3D model. So using this perspective ray trace pooling layer, because we can project the 3D space into 2D space, for example, just like how the camera works, we can enforce that the silhouette that we have taken from our reconstructed 3D model should be as similar as possible to the ground truth silhouette. So in previous works, for example, 3DR2N2, we taught the network so that the 3D model that the network reconstructed is as similar as possible to the 3D model that we have, our training data. But instead, we're taking a 2D picture of the reconstructed 3D model and say that, okay, we have a reconstructed 2D image instead. The reconstructed 2D image should be as similar as possible to the 2D image that we have. That is the difference in this setup. And as Chris just explained in the figure 2 about a lot of restrictions just using this 2D segmentation loss, this reconstruction using 2D segmentation by itself is an ill-posed problem, and that is what makes this discriminator loss necessary for our work. So I guess Chris can explain the rest, combining these two different losses and how we.
By the way, I implement this everything in CUDA, and it's such a pain. to implement this, and then unlike some of the previous works that use the spatial transformer based, which is based on sampling, ours use actual ray tracing, and then use the hit test to figure out which voxel the ray hit, and then we select those hit voxels, and then pull the values in those voxels. So it has some advantages over those sampling-based method, which is that ours don't suffer from sampling artifact, and also ours can uh, process a large space without yeah, increasing the computation time and cost.
Interesting. And what inspired that kind of alternative way of thinking about tackling that problem?
So probably for that we might have to tell you about the history of our paper. So yeah, before so we started this project a very long time ago, and then when we finished the implementation, and then when we started working on the paper, we saw another paper from Michigan came out, and then we realized that we have to do another comparison, and then we despair, but we did the compare with their method, and then that's how we got different implementation than theirs.
Interesting.
So I guess we didn't even thought about using the spatial transformer when we first started, and then we just followed the physics, which is that when you take a picture of an image, the rays, uh, the lights from surface, light from the source reflect from the surface came to the camera, and then we just can see the color on that pixel, and then that is usually implemented in a lot of 3D games as a ray tracing, and then figure out which surface is closer to the viewer than the others, and then choose the color, and then the triangles, mesh triangles, and then that's how
Interesting.
3D games visualized a lot of interesting sceneries on the computer.
Interesting. I haven't. It's my mind is trying to wrap my head around it, which is super cool feeling. So cool work on that regard. I'd love to know what inspired all of this. You talked about the project taking a long time. What all the way back kind of said, hey, this is something that we're interested in researching and starting off the entire research process?
So probably then I have to mention previous work, which is 3D alternative. So in that work, we wanted to, so my advisor Sylvia is interested in the 3D reconstruction, as I do, and then some of the traditional methods have a lot of restrictions regarding what types of images that we can reconstruct and so on. So we want to get away from those. We want to get out from this constraints, and then solve the 3D reconstruction problem. So, and then that's how we first proposed supervised 3D reconstructions. However, in this setting, we have so many additional constraints, which is that the 3D annotation is very expensive. However, there are a lot of 3D CAD models in online repositories, for instance, like the Google Warehouse and Yogi and so on. And then those repositories contain a lot of CAD models. Yet, it is difficult to associate which CAD model to which image, and then to just not go through any of the steps. We just use the GAN as a manifold projector, and then teach them what is realistic and what is not, and then make the generator to make a realistic shape, as well as the shape that closely matches the silhouettes that we provided to the network. So you can think of this problem as a constrained optimization, where we solve the projection loss minimization, which is that we're trying to make the reconstruction uh, silhouettes of the reconstruction as close as possible to the annotations that we provided. And also, at the same time, we want to constrain this reconstruction to lie inside the manifold of the realistic shape. So that's kind of the high-level overview and then the motivation behind our work.
Let me take a moment to say that this wouldn't be possible without companies like Amazon.com. If you have experience with machine learning and are looking for a new challenge, they have over 100 opportunities available. Be sure to check out the link in the description, and let's get back to the show. And you guys had touched on some of the applications of this type of technology, but where does your mind kind of wander in the next few years of this application or this research and being applied to different particular problems?
So I see that this problem could be applied to some of the online retailer websites, for instance, like Amazon's, eBay, and then probably we can apply textures under reconstruction as well, and then provide the detailed 3D reconstruction of the product to the users so that the user can rotate, and then probably combined with the virtual reality can actually use the objects that's being constructed.
And also, it's not only, our lab as a whole is also focusing on a lot of robotics. For example, if a robot has a camera on its head, and if it sees something, robot has to live on the 3D world while it only can see 2D space. And it must reconstruct the 3D world. It should make a sense of how the 3D world works in order to interact with the 3D world. And we're also, as a lab, are focusing on like trying to teach robots to directly interact with the 3D world given 2D images, which is like a lot of like conventional sensors and stuff, and see if we can like automate things a lot better and make our life easier.
Yeah, that's really interesting. I had a guest on who was doing research around taking images of humans in different kind of postures and in situations. So imagine having a left arm up and your right leg out or something like that, and trying to model and better understand in 3D what that body might be. And so we had got a conversation going about how a robot might interface with a human and needs to understand which way, if it's touching it or might touch it, which way to bend it and not bend it, and how this human might be structured. And I would imagine that's true with furniture and boxes and everything else in the world. So that's a really interesting application. So what are you guys up to next? I mean, you talked about working in the lab, and I'm assuming there's research and stuff. So I'd love to kind of hear what's next on each of your plate for the next year or so.
We want to use these kind of reconstruction techniques, use this reconstruction techniques for other projects. For instance, we are trying to use this kind of techniques for semantic scene understanding and joint reconstruction as well, so that we not only understand the environment around the robot or its agent, as well as reconstruct the parts that's being self-occluded or occluded by other objects. For instance, let's say when an autonomous car drives around the streets, then it can observe a side of the car, not the entire car in 3D space. So we have to reconstruct the side of the car that's not visible from the viewer, the agent, and also, let's say if a pedestrian is partially occluded by a car or a building, then we have to reconstruct the rest of the pedestrian so that we can maybe predict what type, how the pedestrian is positioned in the 3D space, or even the car as well. If the car is occluded, and then if the car is trying to make a turn, then it can be dangerous, and then we have to understand this fully better, and then this kind of techniques also could be applied, and then that's kind of the direction that I'm working
And do you feel that humans do this very intuitively? I mean, it's something that I would imagine, a 5-year-old kind of, it's like they see a part of a car and they're able to project mentally what the rest of that car is. And it's obviously one of those challenges I think that humans do really, really well, and probably teaching the machines. And we're in that early phase of doing that. Is that something that you guys kind of
on. Yeah,
think
yeah,
about?
we think so because um, yeah, humans are really good at figuring out the rest of the object just from a part, just from seeing a very partial observation. And this is somewhat possible using neural network, but it's still a very big problem and challenge in this field. And then we think that applying this, uh, and we think that the people or human, just in general, have some sense of the manifold realistic shapes. For instance, if there's a hand, then this belongs to the manifold of the human, and then the rest of the body parts will be positioned somewhat in a reasonable space that follows the physics. Then a lot of constraints, and then we don't see contortionists that often in our life.
Right, right.
So people usually will have certain configurations and so on. So those kind of a prior knowledge, I think, is something that humans are really good at, but neural network, it's something that neural network has difficulty figuring out.
Yeah, it's interesting seeing your guys' visualization. We talked about the green, so like the red and the green and the blue, and thinking about a probability. And I picture myself, if I see a leg, my
Mm.
brain's representation of the other leg and where the other arms and the upper half of the body is probably kind of that distribution of the green and blue
Oh yeah,
thought
right.
process. And I think that that's also probably what causes the illusions from magic. And right now, you have a contortionist who goes in a box and you see their leg. So my brain is creating all the probabilities of where the rest of their body is. And then
Right.
the magician moves the body and you're like, how is that possible? Right. And it's because they're the contortionist breaking
Yeah,
the model,
exactly.
which is a really interesting way of thinking about magic as it relates to your guys' research. But um, cool. Yeah, so I'd love to also hear, John Young, your representation of how you're thinking about your future.
Well, I guess it's not too different from business focused stuff, but yeah, I'm trying to learn more. I'm trying to get this more work on like a robotic space to see if it actually works. But because I think there there's a huge field behind robotics that is not yet solved. While I really believe in the future of automation, and there are a lot of mundane labors that can be automated to make our human lives better. Not just to like take people's jobs or stuff, but actually to help people, and so that people can focus more on more interesting things than mundane jobs. But the complexity of the real world is like a little way too high for a robot to actually smartly interact. That there's a still huge gap in the real world and the robots. And although there are a lot of like perspective in robot human interactions, like social interactions or stuff like that, I guess the most fundamental part of robot interaction is that it has to figure out to do the configuration correctly to not just hit actually on like there's a recent accident in like a Stanford shopping center that like a robot that is meant to like keep the place safe just it didn't detect the human baby and it just ran over a it wasn't a like a really bad accident, but it was just a minor accident that happened. Like we should make sure that those things don't happen for humans to trust robots. So I think that will be. I'm just starting my PhD here, and I still have like 5 years here. And yeah, that'll be my for now like my long-term plan of like can we make these 3D reconstruction like actually applicable in the real world so that we can like automate a lot of parts of our lives and make our lives better.
Yeah, I think the part about humans trusting robots and how high the level of safety has to be in order for us to feel comfortable with it, and talk about level 5 autonomous vehicles, and this idea of saying, what can a vehicle do and not do, and um, humans are super biased and we don't think about things statistically. And so I think that, yeah, you're right. Like the first, even the Tesla accident that caused that guy to die by going underneath the trailer because it didn't fully understand the trailer. The amount of lives saved compared to the amount of lives lost at this particular step in this particular juncture. Although I'd argue Tesla's moving pretty damn fast, but for better or worse. But I think you're right on. I mean, I think the error tolerance is going to be super, super low for society, which is why I think we're seeing, warehouses do it. And then they're trying to not only have the entire warehouse do that, right? So it's like if a robot crashes in a robot, I don't think anyone bats an eye. But if a robot, even comes close to a baby, and as a father of a 9-week-old, I could see the human emotion kick in. I think you're totally right. But I resonate with your vision of the future of trying to continue automation, and I think humanity is often scared of it. I think the Industrial Revolution, I do a lot of reading about the Industrial Revolution and how humans went from, this very labor. They didn't trust the plows and the machines to do the farming. And in hindsight, it was one of the most liberating things for society. So I hope for the same here. But I appreciate you guys hopping on the podcast and also contributing to the community.
Thanks. I hope. Thank you.
Cool. Appreciate it. Thanks for joining the show, and have a good one. See ya.
All right. Thanks for having us, and then take care.
Bye.